Are you loving these videos yet? I hope so, because we are up to video 4. Alright, so for video 4, it says that an object is held in front of a convex mirror. Notice how convex is bolded. The image you see in the mirror is smaller and upright. Smaller and upright than the actual object? Okay, whatever. It's smaller and it's upright. And cannot be projected onto a piece of paper. Is the image formed real or virtual? Give 2 pieces of evidence to support your answer. Hopefully you are capable of answering that question now. Watch video 4, which is what you're doing. So let's do it. Let's talk about how to do this ray diagram. Alright, first thing we would do is draw in our mirror. And I did check the videos, and on the last video you could see this ray diagram paper. So hopefully you can see it. And when I say ray diagram paper, I just mean the dotted line thing and these little tick marks. That's what I call ray diagram paper. I'm going to take credit for that brilliant physics invention. Okay, so what we're going to do with this thing is draw in a convex mirror. I'm always going to put my object on the left and have my image show up on the right. It just kind of keeps it simpler that way. I'm used to reading left to right, so hopefully you're good with that. If you screwed up and drew yours the wrong way, then just put your object on this side. Okay, well there's my mirror. It's not perfectly drawn, but we'll just pretend like it's okay. When you played around with this, when you were doing this flip this concave mirror stuff over, what you hopefully discovered is it didn't matter where you put the object. Anywhere out here, the image always looked the same, in the sense that it was always smaller than the actual object was, and it was always right side up. That means that that image is always going to be virtual, because it's always right side up, and that means we're going to do some of that projecting rays behind things again. Okay, well we're using the same mirror, just flipped backwards, so our focal length is still 10 centimeters, and 2 focal lengths away, which is called the center of curvature, is going to be 20 centimeters. I'm going to go ahead and mark off those distances. So 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And I'm going to do something slightly odd, and that is to mark these off behind the mirror as well. 1. Okay, now that might be a hint or a giveaway that somehow this image is going to appear back here again. It's probably the case, but we're going to still do the ray diagram and find out. All right, as you observed, it doesn't matter where you put the object, the image is always going to be smaller, upright, and virtual. So we can put that object any place you like. Usually if I did this with you in class, I'd have some groups put their object here, some groups put their object here, some groups put their object here, and then we'd all draw the ray diagrams and find out that we get the same diagram every time, that the image is always smaller, upright, and virtual. For us today, since you're just watching this and I'm not there, I'm going to draw my object here. Did I pick this place for any particular reason? Nope. I just needed to put the object someplace. All right, so that's where my object is going to be. Okay, so I want to trace some light rays. Again, there's lots of possible light rays I can trace. So the first light ray I'm going to look at is a light ray that comes in parallel to the principal axis. Surprise, surprise. Oh, stupid smartboard. We'll try that again. All right, there we go. That light ray, we're used to saying reflects off towards the focus. Okay, well that's sort of true, except that this mirror is convex. Its normal line at that point on the mirror is pointing out like this. So that light ray is not going to hit the mirror and reflect down. It hits and reflects back out someplace. Okay, well, to figure out exactly where it goes, I just kind of roughly drew in that normal line. What I'm going to do is I'm going to think about this as kind of being in reverse of the other case. Light comes in, and instead of reflecting down through this focus, it reflects out as though it came from that focus, the focus on that side, because this is a convex diverging mirror. It's going to cause all the light to spread out. So what I'm going to do is draw a dotted line to help me understand that the light's going to reflect out as though it came from this focus to that point. And then I'm going to extend it as a solid line to show that light ray goes outward like this. Okay, that's where the light is going. So that is my first light ray. Okay, the second light ray I usually trace, in my early diagrams at least, came in through the focus, hit the mirror, and then reflects out, obeying the law of reflection. If I do that here, that's going to be pretty much of a guess, and it's probably going to miss my mirror. So I'm going to use a different strategy again. It's the strategy we employed at the end of our last video. Instead of drawing one through the focus, I'm going to draw one that hits right at the base of the mirror. Because right at the base of that mirror, the mirror is basically like a flat spot. It's a curved mirror is really a whole bunch of little flat pieces, infinitely many little flat pieces all tied together. Well, right there, that flat piece is perfectly perpendicular to the principal axis. So it's easy for me to draw and see what angle that should reflect out at. So if this is my angle of incidence here, maybe, this is my angle of incidence here, I'm going to draw a light ray that reflects out at that same angle. So again, I'm just going to eyeball it. If you have an actual protractor, feel free to measure it, but I'm just going to eyeball it and say, well, it reflects out about like that. That looks pretty good. So that my angle of incidence equals my angle of reflection. All right, well, are these two light rays going to meet? If I put my eye out here someplace, so if this light is reaching my eye, will the light that reaches these two eyes, will this ever converge? No, this is a diverging mirror. It makes it spread out. But if this eye receives this light ray, we know that our eyes and brain work together and perceive that light always comes in a straight line, so from some place back here. And that this light ray, my eye would perceive that light as coming from someplace back here. I've already extended this light ray backwards. If I extend this light ray backwards, this green light ray backwards, what I'm going to see is that it appears to be coming from a common location. Those two light rays both seem to originate from that place. That is the location of my image right there. So I'm going to draw in a tiny little candle right there. That's my image. Because the light seems to come from that place if I'm receiving this light ray. The light seems to come from this place if I'm receiving that light ray. Where does it actually come from? Over here. Did these light rays actually converge together? No. That's why my image is virtual. But would my brain and eyes work together to perceive as though the light came from the same place? Yes. So that's how that image gets created. It's really an optical illusion. All right, so my image is upright. It is smaller than the object. It is virtual because light doesn't actually meet there. Light rays don't reflect off the mirror and actually converge to this place. And finally, it is behind the mirror in terms of its location. We'll learn later how to calculate exactly where that is. But for now, we'll just write it as behind the mirror. Okay, and that is our fourth and final ray diagram. Can you do this on your own? This part is, I guess, your additional homework. Hopefully, these videos have been all right for you, and this ray diagram stuff makes some sense, and I will see you guys soon.